Among the most mysterious and awe-inspiring objects in the cosmos are those black holes, regions of space where gravity is so intense that nothing, not even light, can escape. They are cosmic enigmas, distorting space, time, and the laws of physics themselves. But what exactly is a black hole? And how do they form? A black hole is created when a massive star runs out of nuclear fuel and collapses under its own gravity. If the remaining mass after a supernova explosion is dense enough, it will compress into an infinitesimally small point called a singularity, surrounded by a boundary known as the event horizon, the point of no return. Inside this region, the escape velocity exceeds the speed of light. That means even photons, particles of light, cannot escape its grasp. Hence, they appear completely black. But black holes aren't just empty voids. They are incredibly dense, containing immense mass in a tiny volume. A black hole the size of a city block can weigh more than our sun, and the gravitational influence they exert can stretch across entire solar systems. Black holes come in different sizes. Stellar black holes form from dying stars and usually contain a few solar masses. Intermediate black holes, weighing hundreds to thousands of solar masses, are harder to detect but believed to form in dense star clusters. Supermassive black holes, millions to billions of times the Sun's mass, sit at the centers of most galaxies, including our own Milky Way. In fact, at the core of the Milky Way lies Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. It's surrounded by stars that whip around it at incredible speeds, revealing its presence through their motion. But how do black holes interact with the universe around them? Despite their ominous reputation, black holes don't suck things in like cosmic vacuum cleaners. Instead, objects must cross the event horizon to be lost forever. Outside that boundary, they influence matter gravitationally, just like any other massive object. However, when matter falls into a black hole, it forms an accretion disk, a swirling ring of superheated gas and dust that spirals inward, glowing with intense radiation. These disks can shine brighter than entire galaxies, especially when feeding rapidly. Such black holes are called quasars. In 2019, scientists captured the first-ever image of a black hole's event horizon using the Event Horizon Telescope, a global array of radio telescopes working together. The blurry orange ring surrounding darkness wasn't just a scientific milestone, it was humanity's first direct glimpse of the shadow of a black hole. And that's just the beginning. Black holes also merge. When two black holes collide, they produce gravitational waves, ripples in space-time, predicted by Einstein, and first detected by LIGO in 2015. These waves carry information about the most violent events in the cosmos and open a new window for observing the universe. But the mysteries go deeper. Inside the event horizon, general relativity predicts that all matter collapses into a point of infinite density, the singularity. However, at these scales, quantum effects become significant, and our current theories break down. Physicists believe a unified theory of quantum gravity is needed to describe what truly happens inside a black hole. Could it be a portal to another universe? A link to a wormhole? A place where time flows backward? These ideas remain speculative, but fascinating. Stephen Hawking added another twist with his discovery of all-Hawking radiation. According to quantum theory, black holes are not entirely black. They emit tiny amounts of thermal radiation due to quantum fluctuations near the event horizon. Over incredibly long timescales, this radiation could cause black holes to slowly evaporate and disappear. But this leads to the Young information paradox, a major puzzle in modern physics. If black holes evaporate completely, what happens to the information they swallowed? According to quantum mechanics, information cannot be destroyed. Yet black holes seem to do just that. Resolving this paradox could reveal deep truths about the nature of reality, time, and space itself. Some researchers suggest that information is stored in a holographic skin around the event horizon. Others believe it's encoded in the Hawking radiation itself. And a few propose that black holes don't destroy information. They just scramble it in ways we don't yet understand. Black holes also challenge our intuition about time. As you approach a black hole, time slows down relative to a distant observer. At the event horizon, time appears to freeze. This isn't science fiction. It's a consequence of Einstein's theory of relativity. In a way, black holes are like cosmic laboratories, places where gravity becomes extreme, where the known laws of physics collide with the unknown, and where new theories are born. At Infinity Beyond, we believe black holes aren't just astrophysical objects. They're keys to the deepest secrets of the universe. In our next episode, we'll explore something even more mind-bending: wormholes and the possibility of interstellar shortcuts. Could black holes actually lead us to other parts of the cosmos, or other universes entirely? Stay curious and subscribe to Infinity Beyond as we journey into the darkest corners of the universe.